Hello, in this video I will go over some examples of applications of dot product. First example is about finding the angle between two vectors and also the magnitude of projection. So the force acting on the hook at point A is given. Okay, this one. Find the angle between the force vector and the line AO. That's one of the applications of dot product. And then the magnitude of projection of the force along the line. So when we have vector A, vector B, all we have to do is use cosine theta is going to be dot A dot B divided by their magnitude. That's how we can find the angle between them. Here we want to find the angle between F and the line AO. Line AO is not a vector, but we can easily turn it into a vector by turning it into a position vector. So if we find these two and divide it by each other, that should give us the cosine of the angle between them, and rest is easy. So we got to find some stuff. We got to find F, which we already have it. We have to find position vector AO and dot producted by F. We have to find magnitude of F. We have to find magnitude of vector, position vector AO. Okay, so let's just start with position vector AO. Let's make that little table. AO X, Y, Z. A is located at 1, -2, +2. The units are meters. O is located at 0, 0, 0 meters. So position vector AO from A to O. So O minus A. So it's -1I plus 2J minus 2K. If you have doubts, or if you're not sure, if you're not following what I'm doing here, make sure to go back and watch previous lectures on position vectors that I've done numerous examples. So here I'm going to go faster over position vector. I'm not explaining every step, but you got to watch the previous videos. So we find that we have F. Let's find magnitude of F and magnitude of AO. So magnitude of F is 6 squared, 9 squared, 3 squared, and square root of all of that. The units are kilonewtons, and magnitude of F is going to be 11.22 kilonewtons. Okay, magnitude of F. And we got to find magnitude of AO. -1, 2, -2 squared, square root of that. All the units are meters, and this will result in 3 meters. Okay, so I think we got everything. Now all we have to do is to find dot product of F and position vector AO. F is -6I, 9J, 3K, dot position vector AO, which I just found it to be 1I, what was it? -1I. -1I plus 2J minus 3K. or sorry, minus 2k, and the unit are meters. So remember, dot product of two vectors is a scalar, meaning it's a number, meaning it doesn't have ijk. So again, if you're not sure, go back and watch where I started teaching about dot product. So all you have to do is 6 goes to 1 plus, see, there's no ijk, 9, so j, k, k, I, 9 and 2 plus 3 minus 2. This is kilonewtons meter, kilonewtons meter, kilonewtons meter. So the dot product is actually going to be 18. So the angle that I was after, theta, is cosine inverse of the dot product divided by magnitude of those two. This is what I'm trying to do. Magnitude of one is 11.22, one is 3. So 11.22, the other one is 3. So the units work out just fine. And from here, the theta is going to be 57.7 degrees. So this was first example of application of dot product. We use dot product to find the angle between those two. Part B, magnitude of the projection of the force along line AO. Projection, magnitude, so it's a scalar, projection or component along line AO or parallel to line AO. These are all different terms and wording that someone might use. So if you look back at my lectures, projection or component of a force along a certain direction, you gotta just dot product that force dot producted by unit vector of that direction, unit vector of AO. That's all you got to do. Unit vector of AO, so let's find that. Unit vector of AO is just position vector AO minus 1i, 2j, 2k, divide by its own magnitude, 3 meters. So let's dot product these together. I, 9j, 3k, dot 1 over 3i, 2 over 3j, 2 over 3k meters. Same as above, so 6 minus 6 minus 1 over 3 plus, again, no ijk, the result should be a scalar. Look, one side is a scalar, there's no arrows, it's a scalar, the other side is vector. So ijk's get eliminated because I dot I is 1, j dot j is 1, k dot k is 1. 2 over 3 minus 2 over 3 and 3. So the result of this is going to be 6 kilonewtons. There was a shortcut that you could have done too. You have force. In part 1 we found the angle. You could have just simply put magnitude of F cosine of 57.7, and that would have given you 6 kilonewton as well. Okay, so dot product is basically the same thing. What do I mean by that? Remember, I'm going to write it up here. A dot B as a vector was A, magnitude B, cosine angle between them, right? So when you say F dot unit vector of AO, means magnitude of F, magnitude of unit vector, which is 1, and cosine the angle between them. That is why we just simply use dot product to find the component. Okay, let's look at another problem, a little bit more complicated. 300 Newton force. What is this? Magnitude. Acting on the bracket, find the magnitude of projected component. Projected or component of this force along OA. Just like the previous problem. So component of this force, which is a scalar, but the problem is even says magnitude. Component along OA is dot product of the vector and unit vector of OA. This is what we have to find. This is what the problem is asking us. Okay, so we got work to do. We have to find F as a vector. Of course, we have the magnitude of it, but we don't have as a vector. And we have to find the unit vector of OA, which of course means position vector OA divided by magnitude OA. Okay, let's see. So let's first transfer F into vector. So we have 300 newtons. We want to transfer it into a vector. What do we use? Position vector and unit vector. So this is 300 newtons unit vector of AO or OA. That actually helps because eventually we got to find no, F is not in the line of OA, so scratch that. We have to find it based on the components. We have to find it based on the components because the angles and everything is given. Okay, I see now. So let's see. Force F is on an inclined plane like that, 300 newtons and 30 degrees. So let's bring it to, this is same as axis Y, but this is this, let's call this axis, I don't know, T. So this is T, this is Y, because it's parallel to Y, so it's the same direction as Y. So Fy is 300 cosine 30. F of t is 300 sine 30. Okay. Now let's bring ft to x and y. So now let's look at x and z plane. X and z, and this axis t has an angle of 30 degrees, and I just found ft to be 300 sine 30. So fz, so let's see, fx is 300 sine 30. This angle is 60. That is going to be cosine 60. And that is pointing to minus I. This component here, which is fx, and it's pointing to minus x, minus I. F of y, I found it here, it's 300 sine 30, or sorry, cosine 30 j, and f of z, which is this component right there, is 300 sine 30 multiplied by cosine of 30. In other words, it's 150 cosine 30, and that is K, and this is newtons. This was a very good practice of finding component of a vector based on the angle that is given. So first, I found this Fy, because it's parallel to y-axis. Then I found this one, F prime, you can call it, which was along t-axis. And then I brought the t prime, or sorry, F prime to z and x axis. Okay. If you do the math, you're going to get minus 75I, 259J, 129.9 K Newton. So this is my F. Okay. So next, let's do unit vector of OA. Unit vector of OA, I need my little table. I have point O, I have point A, X, Y, Z. The units are all in mm. O is located at 0, 0, 0, and point A is located at, the X component of it is 300. This is also a challenge. So the component of it, the X component of it is 300 plus another 300 cosine 60. I think I gotta draw it for you. So this is Z, this is X, this is 300 mm, this is another 300 mm, but this one has an angle, goes to point A. This is 30, this is 60. So this length, this one is 300. So this length is 300 plus 300 cosine 60. And it's pointing to minus x. So there's a lot that you need to keep track of. That would be 450 millimeters. Then the y component of it is simple, it's 300. And the z component of it is just this length right here, which is 300 cosine 30, and that would be 260 mm. Okay. So I think we need a new page. So position vector OA is going to be minus 450I, 300J, 260K millimeters. If you take magnitude of ROA, you will get 600 millimeters. And unit vector of OA is going to be those divided by each other without any units. J, 260 divided by 600, and K. Okay, which is going to be 0.75I, 0.5J, 433K. Okay, so the angle, find the magnitude of the projected component here. So I'm going to find the angle and then just use f cosine of that angle. Or, so you have two options. One, find f dot product unit vector of OA. Option 2, as practice, find angle between those two, and then just simply use f magnitude of f cosine that angle to find that projection. So find the angle as a practice, and I give you the final answer for the angle. It's going to be 36.1 degrees. Okay, so if we want to do the dot product, f, let me just write it here quick so remind you, f is minus 75i, 259.8 J, and 129.9 K units are newtons. So when you want to dot product these two together, i's component go together, j's together, k's together, without any ijk's. Remember, this is going to be a scalar. Magnitude, projection, component, these are all q's. We know that it's a scalar. So let's see, minus 75.75 plus 259.8.5 plus 129.9 multiplied by 433. And result of this is going to be 242 newtons. And that is the magnitude of the projected component along that direction. Let's look at another problem, a little bit more complicated. A winch at point B is used to slide a box up a chute CD in a warehouse if the component of the force from cable AB in the direction of the chute must be 400. Component along a direction, so it's a scalar. So what we're given is F along chute AD is 400 pounds. A scalar magnitude. Find the force in the cable for the position of the box given below. The chute is parallel to XZ plane. Neglect the size of the box winch. The box is at the base of the chute at point C. Okay, so assume that this point A and B means point A and C are the same. I want you to find and solve this problem when point A is right at the bottom of the chute or at point C. So let's figure something out right away. Let's find A, which is also C, B and D, X, Y, Z units. Okay, point A is located at X of 120, Y of 100, Z of 0 inches. Point B is located at it's given, minus 45, 0, and 130. Point D is given at 0, 100, and 50. Okay. So let's see what we're after. So force AB dot product unit vector CD unit vector CD gives us FAD. And this is given to be 400 pounds, and it's asking us to find force in the cable. Okay. So let's see. Let's find FAB first. FAB is magnitude of AB, unit vector of AB. So not a dot product. This is just simple magnitude. So unit vector of AB, this is what we have to find. Position vector AB, magnitude of the position vector AB. I'm going to do this much quicker now. So our AB is going to be 165I minus 100J plus 130K. The magnitude of position vector is going to be 232.6 inches. That's a unit vector. And put it back in that equation, what we get is force AB is FAB minus 165, 232.6 I minus 100, 232.6 J plus 130, 232.6 K. Okay, the units for this is pound. I have this in this equation. I have the 400. Next step is to go find unit vector of CD. Unit vector of CD, RCD divided by magnitude of CD. Again, I'm going to go much quicker here. Position vector CD is minus 120I plus 50K. The magnitude of CD is 130 inches. So the unit vector is just dividing those two by each other. Hundred, 130, 50, 130. Okay, so I think we're ready to go back to our original equation and put everything in place and find the only unknown, which is FAB. So let's see. 400 pounds is FAB (165, 232.6 I) 100, 232.6 J 130, 232.6 K. This whole thing is dot product by the unit vector that we just found, 120I, 130, 50, 130, dot product. The only unknown here is FAB. So I've done the math, but this is what you're going to get. 400 pounds FAB. Remember, this dot product should result in a scalar. The other side is also a scalar. No IJKs anywhere. It's going to look like something like this. Minus 165, 120, minus 100, 0, 130, 50 divided by 232 and 130. If you do the math, FAB is going to be 460 pounds. So again, the important equation was right here to understand what the problem was asking us. This was the key to the solution for this problem. Okay, let's look at another very similar problem. Chute and a winch and a person pulling a weight up a chute. A worker is using a ramp and a rope to move heavy objects into a trailer. If he applies a tension on the rope BA of 50 pounds, so FBA 50 pounds, what is the component of that tension along the ramp DC? So what we're looking for is find FDC, scalar, component along DC, that actually moves the load up. Assume the load is 2 feet up the ramp at point B. Okay. So first of all, let's find the coordinates. So I'm going to make a table, A, B, C, and D, X, Y, Z, and units. Point A, well, we don't know this distance, and it doesn't matter. I assume this distance is 0. Point A is going to be at 0, 6, 0 with units of feet. Point B is located at, this is something that needs a little bit of calculation. So this is the ramp. This is point C, this is point D, and this is point B. This is 3. Point B is 2 feet up on the ramp. This entire length is 5 feet. This entire length is 4. So we want Z and Y of point B. Y and Z. So we got to use similar triangles. Z over 4. So Z, this length over entire length, is the same as 3 over 5. Three over 5. So from here, Z is going to be 12 over 5. For Y, I can write Y over 3, this length over this, is the same as 2 over entire length, and this will result in Y of 6 over 5. X of point B is located at 4 feet. Again, remember, I assume that this distance is 0. It doesn't matter. You can assume it 10, 5, 20, 100, any value you want, or you just put it at 0. Does not matter. Point C is located at 4, 3, and 0. Point D is located at 4, 0, and 4. All of the units are feet. Okay. The first thing I got to do is So here, let me write the major equation that we need. We got a dot product BA by unit vector of DC. This is a major equation, so we know what we are after. So we have to find FBA from the magnitude. So FBA is that 50 unit vector of BA. And then I have to find unit vector of DC. So these are the two major things that I'm after. Let's just start with unit vector of BA. Is 50 pounds unit vector of BA, which is RBA divided by magnitude of BA. I'll let you do the math. This will result in 2985 I, 3585 J, 1798 K units of pounds. Next is unit vector of DC, position vector DC, magnitude of RDC. If you're still a little bit slower on position vector, that means you need to go back, look at the lectures on position vectors and do more examples on position vectors. I've explained position vectors and unit vectors in previous lectures, so you got to watch that if you still have questions or you have problems. And this is going to be 3 over 5 J plus 4 over 5 K. And there's no units for that. So now that I found those two, I can put it back in my major equation here and dot product those two together. So let me write this quick here for reference. 2985 I, 3585 J, 1798 K pounds. Unit vector of DC, 0 I, 3 over 5 J, 4 over 5 K. No units. So dot product of these two is going to be I goes together, no IJK. 3585 goes to 3 over 5. And 1798 goes to 4 over 5. The unit on first one is pounds. The second one doesn't have any unit. So the final number is going to be 3583 pounds. 3 significant figures. 35.8 pounds is the final answer. Let's look at another example. The slider shown weighs 30 newtons, this W, and has been glued to the rod in an assembly. It is known that the glue will fail if the force on the slider parallel to the rod exceeds 20 newtons. So if F in the direction of AB is bigger than 20 newtons, it's going to fail. That's how much the glue can hold. Will the assembly be able to support the slider if it's held in the position shown? So we have to find component. In other words, find projection or magnitude or component of W along AB. This problem could have been like this. This is exactly what it's asking us. So to do that, to find projection of the component of weight, we have to use dot product. We have to dot product the force by unit vector of what? Right, A, B, or CB. It's going to be the same. So let's see. How can I transfer the weight into a vector from its magnitude, which is 30 newtons? Do I know the direction of weight? Yes, I do. Weight is always going straight down. So it's 30 newtons is the magnitude. Straight down is minus k. So 30k is my weight. Unit vector of AB. I need position vector divided by magnitude of position vector. That means I need my table of A and B, coordinates of A and B. So A is located at the 0, 0, and 70 centimeters. B is located at 40 and 40 and 0 centimeters. So the unit vector here is going to be 40i, 40j, 70k divided by the magnitude, which is going to be 90 centimeters. Last step is to do dot product. So dot product of these two AB is going to be I goes to I, so 0, 40 over 90, plus J is also 0, 0, another 40 over 90, and then K is minus 30, the other one is minus 70 over 90. No IJK, remember this is a scalar, no IJK whatsoever, so it's going to be 23.3 newtons. So what happens? That's right, the slider fails because the force along the rod is exceeding the amount that glue can hold. Let's look at another problem. Find projected component of F acting along the axis AB of the pipe. Find projected component. Projected component. Remember, magnitude. Now you should be getting familiar with that term, projected component along a line. That means using dot product of that force by unit vector of the direction. This is the governing equation. This is the main equation that we're after. So now let's see what we have and what we don't. So I don't have F. I don't have F as a vector. All we have is magnitude. So I have to find that first. To find that is that magnitude, and then let's call this point D. And I need to have unit vector of AD. Okay. So I want you to pay attention here before we move on. This is a dot product. As a result, it will have a scalar, because I've seen a lot of students get confused on these two. This one is not a dot product, it's a simple multiplication. Because, and result of it, this is not dot product. Result of it is a vector. This is when you have a force of 80 newtons or a force of known magnitude, but you don't have it as a vector. To turn it into a vector, you just add a unit vector next to it, or multiply it by unit vector, so you add the direction to it. What we are doing here, we are trying to find a component of a force by using dot product. So it's good that these two equations are next to each other so you can compare them with each other. So it turns out we need points A, B, and D. So let's make a table. A, B, C is at 0. I don't know if we need it or not. X, Y, Z, and units. A is located at 6, 7, minus 2 meters. B is located at 0, 4, 0 meters. C is located at 0, 0, 0. And D is located at 0, 0, minus 12 meters. Okay, so unit vector of AD, position vector AD, divided by magnitude of position vector AD. Gonna go a little bit quicker here. It is going to be minus 6I minus 7J minus 10K divided by 13.6. Okay. So therefore F, if multiple everything by 80, is going to be minus 35.28I minus 41.16J minus 58.8K. The units are newtons. Okay, we got that out of the way. Next, we got to do unit vector of AB, position vector AB divided by magnitude of that position vector. And this is going to be minus 6I minus 3J plus 2K meters, and the magnitude is going to be 7 meters. I think we're ready to do the dot product. Dot product, I's, J's, and K's. The result is going to be a scalar. No IJK should show up in the result. So FAB is going to be not sure if my final answer is correct, so please check my math here. Is going to be 35.28 minus 6 over 7 plus 41.16 3 over 7 plus 58.8 2 over 7. So please do the math. I have the answer of 19.7, but I'm not sure about it. So not sure. But that's what I got. So up to this point, it should be okay. Please do the math, figure out if my answer is correct. Thank you.